All right, this is a different kind of video for me. I'm going to try to give a guide to the math major. So a lot of people want to learn math, but it's not obvious what's important or how to approach subjects. I'm going to give recommendations for courses and books that will take you through the whole thing, a whole undergraduate education in math. I was inspired to make this video after I came across a whole bunch of similar videos about the math major or how to learn math on some other channels, and I'll put links in the description. Um, After hearing them, I guess, well, here's what I'll say. They're not wrong, because what they did worked for them, but I guess my perspective turns out to be very different, and I hope I can help some people. So I hope I can help people in high school who are thinking about studying math, or people just starting out in a math major, people who want to learn math on their own. Maybe there's people further along in math, and maybe we can see if we agree, and maybe some professors on some curriculum committees will see if they think I have the right idea. I'm going to talk about the following subjects: calculus, single and multivariable, ordinary differential equations, linear algebra, real analysis, partial differential equations, complex analysis, number theory, algebra, probability and statistics, topology, differential geometry, and algebraic geometry. That's not all of math, just the basics from start to finish. So I'll talk about those subjects and give some general advice at the end. All right. First, calculus. Everyone has to learn calculus. Everything that changes in time or space is represented by functions. Everyone has to know the relationship between the speedometer and the odometer. Probably a lot of math majors in US colleges and universities today probably took a course in high school, but no matter if you didn't, there's nothing wrong with what I think is the most popular standard text in this subject, James Stewart's calculus. And you want his version with early transcendentals. Early transcendentals means that the non-algebraic functions, the exponential function, the logarithm, and the trigonometric functions are introduced early, before maybe you have all the rigorous apparatus to define them properly, but you need to learn how to use them. I think that's the right approach. If you are the kind of person who is not satisfied by, at some points in the book, it says this will not be proven, and you feel like you're being hoodwinked, you could learn calculus from this book, Calculus by Spivak. Here's a book that proves all the theorems in calculus. That overlaps quite a bit with what you'll see in a real analysis course. So it's not strictly necessary. I think it's really a matter of preference. Let me recommend something else. Calculus has been written and rewritten so many times, and there's always this tension between needing to compute and learning things quickly versus a rigorous approach where everything is properly defined and everything is proven. You can sort of throw all that aside if you take a historical approach and ask, how did people actually do this? I highly recommend this book by Otto Toeplitz, The Calculus, a Genetic Approach. That term, the genetic approach, refers to the genesis of the subject, the development of the subject. How did it look like to the people who actually did it? So there's a very confusing issue. How do you introduce the exponential function? There's ways to do it rigorously, but it's highly unmotivated. But look at the way it was actually done when people were trying to make logarithmic tables for calculations in astronomy. Totally different perspective on the subject, extremely useful for anyone who wants to do math, because it will show you how problems are actually done. All right, let's talk about multivariable calculus. You're not done with calculus because the world is not all on a line. Things exist in 2, 3, and there are models of things in higher dimensions where there's a lot more geometry, so there's a lot more to be done here. You can continue with Stewart's book. I think that contains another year's worth of calculus there, in the multivariable calculus. This is the book that I learned from, Advanced Calculus of Several Variables by C.H. Edwards, Jr. There's also another excellent book by Bressoud on this subject, Second Year Calculus from Celestial Mechanics to Special Relativity. Again, these are the problems, orbits of planets. These are the problems that people were actually trying to solve. Will be a consistent theme in my recommendations. This is a hard subject to cover in one semester. I guess different programs have different needs. Maybe people want to cover the whole thing in one semester. I find that very rushed. I think there's nothing wrong with taking 2 semesters, one for the differential multivariable calculus and one for integral multivariable calculus. That gives you time to think about things like, well, how do people actually optimize functions in practice? I mean, this can lead you in many directions. I think in the future, people will use a lot more computer graphics and animation, both for exposition and teaching of this subject and training people to do things. That should be a part of this course, I think. Differential forms, there are a lot of professors out there who take it as a point of such pride that they introduce these things called differential forms in their multivariable calculus classes. This is a formalism. It helps to generalize things like the gradient, curl, divergence, and the change of variables formulas to higher dimensions. But if you understand them in 2 and 3 dimensions, that's all that you need right now. When you need them, they'll be there for you. I don't like the introduction of formalism for its own sake because someone else uses it down the line. What you really need to be able to do is answer those problems of celestial mechanics or something like this. I mean, people who study physics and the theory of electricity and magnetism out of a book like this, Introduction to Electrodynamics by Griffiths, that's the test of whether you really understand multivariable calculus. Differential equations. So you're not done really with calculus. I mean, what do you use it for? The functions that actually we want to know about in the real world are not these elementary functions, are not simple functions, the examples that you learn in calculus. They're known to us mostly through the differential equations that they satisfy. And it just so happens that, well, differential equations are very hard in general, but if we can separate out the differential equations in one variable, they have a much nicer theory, a much more complete theory. There's a local existence and uniqueness theorem. There are lots of cases where there are explicit solutions. This is just a very nice, should be a very leisurely class, honestly, after multivariable calculus, which has a lot of tricky stuff in it. Probably a lot of scientists and engineers are getting a lot of this material in their own classes, but it's very good. It's very important for math majors, even if it's a simple class, to take a course in ordinary differential equations. The only prerequisite is calculus. I have no problem with a very standard text like Boyce and DePrima's elementary differential equations and boundary value problems. I've taught a couple of courses out of that book. After a course in ordinary differential equations, you'll be able to go in a lot of different directions. There's a lot you can do. Don't ignore numerical methods. This is a big mistake, I think, that I made, and it's very easy to do because it doesn't exist a whole lot in math departments if they're really focused on pure math. But it's really still a part of math. You should know how you learned the theory. How do people actually use it? How do people actually get computers to compute? How do people actually solve in practice these differential equations? That could be a whole different course. You can also go on to learn a lot about classical mechanics and dynamical systems. And of course, this is necessary background when you want to study the general case of differential equations in higher dimensions, which is partial differential equations, which is a more difficult theory that's coming later on. All right, linear algebra. No prerequisites. You could have started with linear algebra, but I think it's good to have it now. This is a course I did not appreciate when I first took it, just how ubiquitous this subject is. Now, you've probably seen a lot of it actually to this point because the derivative of a function of several variables is a linear map, and the change of variables involves a determinant, and there's plenty of linear algebra in the theory of ODE. You could have taken it first. It's just a matter of preference. I actually prefer to see lots of examples that require a theory before I learn a theory itself. But this is a theory that you'll actually need and use all the time, pretty much no matter who you are, because everyone needs to solve linear systems and learn how to decompose or decouple linear transformations and vector spaces. I learned this subject from on a course using a book, Linear Algebra by Hoffman and Koons. That is a very pure math-oriented book. All of it's abstract. I mean, it proves all the theorems, but there's no applications. That's not the way I would learn this subject today, honestly. I think I gave that book away. I'm sorry, I don't have physical copies of all the books that I'm talking about. I've looked at a lot of linear algebra books. A book that most closely resembles how I think of the subject and what I think is important today would be a book by Strang, Linear Algebra and Its Applications. Once again, do not miss out on the numerical and computational aspects of this subject, because this is what people actually do outside of math. Again, it's a completely different perspective on the subject. It will help you understand it in a completely different way, and much better, because it's more concrete. It's more how do you calculate, which is the most important thing. Although, of course, in this course, you do need some very important theorems. And it's very unfortunate that I can't recommend a genetic approach to this subject that covers things like, people were solving linear systems 2,000 years ago, but the theory of determinants and resultants, and or 19th century algebraic geometry, and also the principal axes theorem and Cauchy's interlacing polynomials to show that symmetric matrices could be diagonalized. Someone should write that book. But once you're finished with linear algebra, there's so much you can do. You can learn about numerical methods. You can certainly go to Strang, another book by Strang's, Linear Algebra and Learning from Data, which will teach you what of linear algebra helps you to do machine learning, which is so popular today. Everyone should know about that. I also like this book by Demel, Applied Numerical Linear Algebra for Numerical Methods. Let me make a comment. There are a lot of different courses out there. Some are called Honors Linear Algebra. If your course is too abstract, and you can tell if your course says something about rings or modules, or there's a lot of exact sequences or commutative diagrams, you are in the wrong place. That course is not useful. They are taking something which is very concrete and putting it in a language that is just more obscure and meant to handle certain cases, which if you actually ever need them, you can learn it then. Most people will not. So I would just say, walk right out of that class and you'll be doing yourself a favor. Let me talk about a class on proofs. There are a lot of programs that offer what they call a proof, introduction to proof theory, or something like that title. That is not a subject area in mathematics, of course. They just want to initiate students into the habit of writing out proofs. Now, I think that people know on some level that you have to prove the things that you assert, and that's what you do when you do a calculation as well. And you need to learn how to communicate. And I think that comes about when you learn actual content and you see how people have proven other things. Now, a lot of people disagree with me and think students need this. I think take it only if you feel you really absolutely need it. I don't know what sort of content, I don't know how you can prove things without there being something to prove, and it's usually a mishmash of some topics. I think learn the subjects themselves and you will learn how to prove things, trust me. Okay, we come to the cornerstone of an undergraduate math program, a course on real analysis. You can take this course as soon as you've had calculus and multivariable calculus. I think it's probably best if you have it after ODE and linear algebra. What is the point of this course? It would probably take me a whole video to describe, well, what is the difference between calculus and real analysis? Some people say real analysis is just a rigorous version of calculus where you prove things. In some sense, that's true. It's only because calculus has been rewritten to include a much greater scope of all functions of a real variable and continuous functions, things that Newton never really thought to consider. You could do calculus very differently if you were just thinking about power series. Real analysis is really about resolving the crisis caused by Fourier's introduction of infinite trigonometric series solutions to the heat equation, and figuring out when do limits of functions exist, and also limits of real numbers. And so real analysis is a story of 19th century work to resolve that crisis that took almost the whole century. Uh, you will not see that story in the standard text. Here's a standard textbook for this subject, Principles of Mathematical Analysis by Rudin. It's not a bad book. It has several things going for it. It's very concise. It has very clean proofs of all the theorems. It has good exercises, which is rare. You know, and old books that have been worked over many, many times. That's something that is to their credit. But it has no motivation whatsoever. It does not tell you why you should be paying attention to those things. It does not tell you what these things are used for later. And that's what makes it hard to learn from, in my view. This is the book, I think I found this book. This is the book that I probably learned the subject from, Real Analysis by Hauser and Sullivan. At least it contains an exposition of Cauchy sequences. And there's lots of other analysis texts. But if you want a very different view, the kind of view that I think really helps you, again, by David Bersoud, he has a book called A Radical Approach to Real Analysis, which again describes for you how it was done, what was the development of this subject. It will train you to think like a mathematician, the way that a book with finished definitions, the definitions that came 100 years after Fourier, you know, he didn't have an exercise in a book to say, show that this definition shows this. He had to work out the subject from examples. You could benefit from learning it both sides. Another view, something else, another way that's legitimate to learn this subject. I really like this book by Davidson and Donzig, Real Analysis and Applications, Theory and Practice, because here's people actually using it, especially they have a lot on approximation theory, which is a very important subject for scientific computation. It has been for a long time, totally obscured and completely missing in Rudin's book. That is a great way to learn real analysis. A lot of programs have a second semester of real analysis that will focus on measure theory, Lebesgue integration, and Hilbert spaces. And my advice is you don't need that course at this point in your career. I am always of the view that you don't need theory for its own sake. You only want theory for doing things. And a lot of math students who are full of zeal for learning math, they think they've heard of this thing, the Lebesgue integral. They think it's somehow more general than the Riemann integral, which is not strictly true. And they think that it's good to learn about it for that reason. That's totally ridiculous. The reason that it was so important is because it allowed for a more robust theory of convergence of Fourier series and solutions of partial differential equations. Only when you are at that crisis, that's a time to learn that subject. Also, if you study the theory of probability, then you'll need the theory of measure. That's when you need it, but not now. I would not learn that subject until you need it. Okay, well, now you're all primed to learn one of the great subjects in mathematics, partial differential equations. It's not really even a subject. It's like a running theme. Everyone has to, everything in the world is described with differential equations, and there's no single theory that addresses them. Somehow each equation takes on its own life and has its own theory to address it. There are some themes within that subject, and especially if you're studying the beginning and the origins and the first equations that people were able to solve, this is what you'll do in an undergraduate PDE course, basically learning what people figured out about PDE from 1750 to 1900. Things like the geometry of characteristics and the wave, heat, and Laplace equations. I happen to like what is actually a pretty standard text for this subject, Partial Differential Equations, an Introduction by Strauss. I've taught out of this book. I think it's a very understandable book. I think it fails in just one respect, that it's missing proof of the existence of a solution for the Dirichlet problem for the Laplace equation. And I think the instructor should supplement with Perron's method to do that. And then you'll actually use the Arzela-Ascoli theorem, which should be the culmination of your real analysis course. And then you'll really have a lot, you'll be primed to study partial differential equations more seriously later on. Again, that book will only have one chapter and really just an invitation to the subject of how of numerical methods and how people solve partial differential equations on their computer in practice, find approximations. That is its own subject. That is something you, again, should not miss out on. There's no reason, there's no, in my mind, such a hard and fast distinction between pure and applied math. This is what you have to do. That's the problem in front of you. So you have to find a way to do it well. That's something you should do, but I don't have a text to recommend. Now, a companion to that course, could be its own course, would be a course in Fourier analysis. So this is a book that I got very early. I love this book. Fourier Analysis and Introduction by Stein and Shikarchi. This was such an inspiration to me, learning about Fourier series, starting from a vibrating string, something I could appreciate, to this whole theory, basically applying linear algebra and sometimes in infinite dimensions to these equations, and how powerful this theory is, which of course you will see to some degree in a PDE class. And you could have a course on Fourier analysis. It will overlap quite a bit probably with that course on PDE, because you can use Fourier series methods, but you should also cover the Fourier transform, the Redon transform, and medical imaging technologies, and things like discrete Fourier analysis, which can help, which can lead you to some analytic number theory. Maybe you also go from there to signal processing and wavelets. There's just so much you can do with Fourier analysis. This book, honestly, everyone should get this book. If you haven't learned this subject already, and even if you have, there's so many great exercises. This will train you to be a mathematician. Wonderful book. Can't miss out on this. And great theorems that should be used to supplement a course out of Strauss anyway. Complex analysis, another great course. Probably you want to have your course in real analysis first. Now, you're probably familiar with the complex numbers because you need them in order to solve algebraic equations. You need them to understand more fully the theory of power series. But of course, it's also needed for things like PDE and 2D and conformal mapping. And besides that, it's just such a rich theory. It's more rigid than is real analysis, because it turns out complex differentiability implies basically solving very rigid differential equation. But it has so much varied behavior, as evidenced by this thing called the Riemann mapping theorem. I learned this, this course out of this book, Function Theory of One Complex Variable by Green and Krantz. Very nice book, very easy to read, and lots of great exercises. You can really master complex analysis from this book. Maybe a more classic text would be this book, Complex Analysis by Alfors. But they differ really only in some of the, in the exposition and some of the advanced topics. A book that I would recommend today, just because it contains more of what I think is important, is this book, Complex Variables by Ablowitz and Focus. And once again, if you look at the numerical methods in complex analysis that people actually use, it will give you a totally different perspective, and tell you what's important and what you have to pay attention to than any of these. There is this 3-volume magnificent set by Henrici, Applied and Computational Complex Analysis, that I've actually had to use quite a bit. Wonderful stuff, and sections on radio and solving for conformal maps and all kinds of things. That is great stuff. Do not miss out. And there's lots of directions you can go after complex analysis, which you will need for number theory, certainly, and some other things. Learn about the theory of elliptic integrals and elliptic functions. A lot of people miss out on this subject that drove a lot of 19th century mathematics and ultimately geometry, and leads to the theory of Riemann surfaces. And it's so important for number theory as well. I don't know, is there a great book? The book that I've used which because it's so nice, it contains, there's so many confusing formulas, Elements of the Theory of Elliptic Functions by Akiezer, after a course on complex analysis. If you want to check that out, there's plenty more to be done. And of course, there's so much analysis of the Riemann hypothesis and whatnot. So everyone should learn complex analysis. Switching gears to a different kind of theory. We've talked about a lot of analysis. Let's talk about number theory. It is possible to be a professional mathematician and not know anything about number theory. You could certainly say, I don't care about the distribution of prime numbers. That's just some abstract concern. I care about fluid flows or what have you. That's defensible. You can say that. But you'd really be missing out on a subject that has driven so much of the development of mathematics. And it's clearly a good theory. Why? Because there's so much rigidity. There's things that are simple to state. There's divisibility and symmetry, and yet there's so much complex behavior. There's so many questions to ask. There's just so many things to do in number theory. I think you're really missing out if you completely don't learn any number theory. Let's assume that you want to do number theory, even though it's not required, I think, in every program. Where should you start? Now, I got my training in number theory at this wonderful summer program for high school students called the Promise Program at Boston University. That was my mathematical boot camp, where we did problem sets every day with no text. That's really the right way to do it. But if you can't do it that way, I recommend this wonderful book by Hardy and Wright, An Introduction to the Theory of Numbers. Boy, there's a lot there. It moves quick, but it does start at the beginning. Also, a thing that you could do, there's nothing wrong with starting from one of the sources, you could say. Here's Gauss's Disquisitiones Arithmeticae. And yeah, it's old, but it starts at the beginning, and you can see this is Gauss, figuring out, solving everything about congruences and solving equations, modulo various numbers. And then he does some more advanced stuff, much more comprehensible than a modern treatment in many ways. And you can see, of course, how he solves it. What do I really recommend, though? There is a book that I truly love. I'm so grateful that there is a book like this. Fermat's Last Theorem, A Genetic Approach to Algebraic Number Theory by H.M. Edwards. H.M. Edwards is another one of these mathematicians who appreciates that you should learn about the development of a subject, not how it was written afterwards, not all the formalism and the general version, but the problems as they appeared to people and how they did it. And that book will give you such a better perspective on how to calculate, how to solve, how did people really think about these problems of is there unique prime factorization in cyclotomic number rings. Fantastic book. That's the way you should learn, maybe in your second course, could possibly be a first course in number theory. It starts at the beginning. I mean, another friendly exposition of some of that stuff, and a second course in number theory would be something like this book, Algebraic Number Theory and Fermat's Last Theorem by Stewart and Tall. You don't need too much machinery. You don't want a graduate level text for number theory. You can certainly take 3, maybe even 4 semesters of there's so much number theory to do. It's all wonderful. And of course, it's going in so many directions. Even people who are not interested in totally abstract questions, number theory is used. It's used everywhere in our cryptography. That's one direction you can go. Also, there's something called coding theory. How do you encode information in a good way? Maybe after you've had some other group theory that might be useful. And of course, after this, a course on number theory, a couple of directions to go. You might want to learn about the theory of the arithmetic of elliptic curves. There's great books by Silverman and Tate, Rational Points on Elliptic Curves, and a book that I really like by Knapp, Elliptic Curves. And of course, now this course, is not to be had after all those other courses. I'm just doing this in a linear order, but number theory you could have taken a long time ago. Once you have had some Fourier analysis too, that really opens up a lot of the using analysis and doing analytic number theory. All right, let me come to the other major part of a math major, usually one of the only required courses in algebra, or sometimes called abstract algebra, modern algebra. It's not quite the same thing as the algebra that you hear about that you learn in high school. By algebra, in this sense, they're no longer talking about algebra, adding like terms to an equation to both sides to put it in a different form. They're talking about structure. They're talking about a 20th century view of mathematics in which we're looking at objects with a kind of structure. And most places, most programs will have you do a course in groups, rings, and fields. Those are three different mathematical objects with some structure and things you can prove about them. Now, here's the thing. You could take a course like that and easily not learn anything I think is really valuable. It's so easy to completely miss the point just learning about structure as though structure for its own sake was the point. What is the point? People were trying to solve polynomial equations. So let me do a comparison here. Here is a book, here a once standard text. I don't know if people are using it so much anymore. Abstract Algebra by Dummon and Foote. I have this old edition. It's a gigantic tome of algebra, probably the equivalent of at least 5 books. And you could learn a bunch of theorems about groups, a bunch of theorems about rings, a bunch of theorems about fields in a semester of algebra and not have any clue why, what's the point, what is this all for? And you'd be right to ask that. That is the right question to be asking. Now, here is a book, much older, before people thought that they should rewrite the subject just to emphasize abstract structure. L.E. Dixon's Introduction to the Theory of Algebraic Equations. And this is an actual exposition of what people were trying to do from the 16th century, solving the cubic. I mean, everyone knows the quadratic formula from 4,000 years ago, but the cubic was only solved in the 16th century. People were able to solve the cubic, the quartic, and then they worked on the quintic, and something didn't quite work out the same way. There's a story here about where symmetries were found, the roots of the resolvent polynomial, how many there were, and the original polynomial you want to solve. That's the story you want to learn that leads to the work of Lagrange, Abel, Ruffini, and Galois theory. I say start there because that's real mathematics. It's not theory designed to address that. The real book that you want, though, even better than the Dixon book, is another book by H.M. Edwards. H.M. Edwards is Galois theory. That book is fantastic. Again, this is a development of the subject. It's so easy. You can look at that book by Dummon and Foote and have no idea how did Galois come up with this when he was 19. Well, the subject didn't look like that to him. But when you see what he actually did and how he thought about things in terms of permutations of roots and identified the key issue of normal subgroups, this is how he developed that theory. If you take a course like that, you will know so much more. You will have so much more valuable work and technique and insight into the subject than anybody who takes a course on the pure algebra, groups, rings, and fields. By the way, I mean, groups and fields form a part of that Galois theory. Rings, what is that for? For number theory, for a view of algebraic geometry? What are you learning this theory for? This is the question you should be asking yourself before every course you take. That is not the way to learn algebra. Learn it from H.M. Edwards, Galois theory, or L.E. Dixon. That's the better way to do it. There are some other treatments. I think this guy, Stahl, Introductory Modern Algebra, Historical Approach. That's another one. But I really love that book, Galois theory. Now, some programs will have you do a second semester of algebra, usually on Galois theory. I can't imagine how you could take a course on groups, rings, and fields and then not learn about Galois theory. I think you should do the Galois theory first. But I think now what more should you do? Once you have Galois theory, now you have a reason to study groups of symmetries and symmetries that act on things. Now you can do a serious investigation into finite groups. It would be great if you could throw in at this point a study of the continuous symmetries of space, something that certainly people in physics and probably engineering need to think about quite a bit. That's a little bit tricky because you need maybe a little bit of differential geometry and differential equations to think about those things, but not too much. And I think a coherent treatment, especially also discrete subgroups of continuous groups and representation theory. That's something that a lot of people need, especially everyone taking quantum mechanics. I guess, how could you do this? I learned that subject from a variety of sources. People in physics can try their hand with this book, Georgi's Lie Algebras in Particle Physics. Also, I think for a whole lot more, Fulton and Harris, Representation Theory of First Course. That's really what you should be doing, I think, if you're learning abstract algebra, not a bunch of stuff. A representation theory, I should say, is a systematic way of studying symmetries acting on objects. And it turns out that there's so much rigidity that you can end up saying a lot of things about the objects you're studying. And it opens up a whole, it's a huge theme in mathematics. It opens up a lot for you. That's my view on algebra, somewhat controversial. All right, next, probability and statistics. I'm going to talk about them at the same time. These are not my areas of expertise, I have to admit. You probably only need calculus to study probability, although maybe statistics, you might want some linear algebra, maybe some real analysis. Do not miss out on statistics is basically what I'm trying to tell you. Just because it's not necessarily in a math department, that's because somehow the sociology of the field has gotten to the point where sort of pure mathematicians don't do it. But of course it's a mathematical subject and it's a key discipline in experimental science, and so is probability. I mean, okay, so how should you learn this subject though? It's not going to the works on a modern theory of probability based on measure theory and the theory developed by Kolmogorov in the 1930s. There's so much that came before that, things like expectation and the law of large numbers and inverse probability and the central limit theorem. Everyone should learn, why is this normal curve called a Gaussian? What did Gauss do? How did he figure this out? These are where maybe you should start. You think 400 years ago, you could have gone into a casino and suggested a game and could have won a lot of money because they didn't understand the right betting strategy, things that we know now. I recommend this. There's a fantastic book, Classic Problems of Probability by Gorochern, and that is an exposition of lots of these problems and how people solved them. That's maybe where you should begin. And there's plenty of places to go with probability. Before you need any of that theory. There's so many problems about probability on graphs and other kinds of combinatorics, Ramanujan graphs, Ramsey theory, things that are important in computer science that a lot of people use. There's statistical mechanics and percolation. There's discrete time models of finance. All of that you can approach and see how far you get learning real stuff before you need measure theory. When you need it, it'll be there. That's the way to do it. When it comes to statistics, of course, maybe now you're talking about how do you learn from data? How does data tell you something? And also, how does data help you to change your prior assumptions about distribution? So these two subjects go together. And of course, statistics is key for all experimental sciences. And it's key for the major technology of our time, artificial intelligence, and also finance and sports betting. I'm not an expert in statistics. I happen to like this book, All of Statistics by Wasserman, but I'm not an expert. I don't know the right way. You need to maybe consult a statistician, but I'm just telling you, don't miss out on statistics is the key takeaway at this point. Okay, now the rest of these subjects are more like a a little bit more specialized. Not everyone needs all of them. So let me talk about the subject of topology. In the 19th century, people called this analysis situs, the study of spaces where you forget about the geometry itself, but only how it can be moved when it's somehow smoothly or continuously deformed. And this helps you to derive some coarse but robust classifications of surfaces, manifolds, various kinds of objects. There are multiple origins of this, this study. There's graph theory. There's the famous problem of Euler and the bridges of Königsberg. There's combinatorics of polyhedra. You've probably seen some topology now, both in real analysis, what's now today called the topology of Rn, but also the winding number in complex analysis. If you've seen some differential equations with some singularities and what happens when you have to avoid them and go around them with a curve, or if you continue with complex analysis to the study of Riemann surfaces, there are invariants like the genus of curves and things like the Betti numbers for higher dimensional manifolds. Poincaré is one of the originators of this subject. He had his own, you should look at what he said he had to deal with. He was looking at the three-body problem. So this problem also comes from dynamical systems and looking at things like discrete subgroups of continuous groups, he said. Now, here's the thing. I view this as an auxiliary subject, not to be studied on its own. There are some people who study topology for its own sake. I know some people who read about this chart of computing the stable homotopy groups of spheres and thought that was so interesting that they would devote their career to that problem. But I think most of the interesting problems involve that geometry, involve metrics, involve differential equations. So what do you need topology for? You should probably not take a topology class until you have a need for it. And probably a lot of the topology you'll need, you can probably pick up in those particular courses. Probably a lot of the topology I needed when I worked in complex manifolds, I probably got from Griffiths and Harris's book, Principles of Algebraic Geometry. I did take a course once where this was the book, Algebraic Topology by Alan Hatcher. It's a very popular book. I think we went through chapters 0, 1, and 2, and I've honestly have never used it, never. So I strongly recommend not taking a course in topology, honestly, until you have taken any one of those other subjects that forces you to consider topology. And that will tell you what you really need much better than I can recommend. And I'd say the same thing about courses labeled functional analysis, by the way, that study fine properties of functions for its own sake. And actually some of that theory might be quite good, but you really only need it if you are studying an equation where you need that theory of functions to help you find weak solutions or whatever. So don't study the theory on its own. So I would strongly recommend just until you need topology, forget about it. You could probably learn about the genus and whatever else if you're studying manifolds. And if you study number theory, people have tried to work topology in there. You can judge for yourself whether how important, how much it actually helps you to have the topological viewpoint. All right, differential geometry. Here's a subject I really like. And it's a pretty classical subject where you really only need multivariable calculus and ODE to get a start in this subject. The origins of this subject are quite old. I mean, you can think, how did Mercator make his map? He knew that the world was round, but he wants to project it onto a flat map and actually accurately represent angles when you want to sail a ship. So differential geometry is all about finding the closest thing that you can to straight lines on curved spaces, and this thing called curvature and how it affects the global geometry. Now, a lot of people will be coming to this maybe from physics, especially because general relativity is all about differential geometry, and so is quite a lot of other modern physics. what you want at this stage is a very concrete class, a class just building from examples, explicit examples of maps, of surfaces, of computing, learning how to compute. That's where you'll need your differential equations, how to compute geodesics, how to compute the curvature, and doing it over and over and getting a feel for the subject. That's what you need out of a class, not a class with too many abstract theorems. What you want to come out of this class is having computed the curvature of a lot of spaces and not being able to say, oh, a manifold is a second countable Hausdorff, whatever it is. That is not important. What's important is being able to do something, and maybe a couple of theorems like the theorem egregium and Gauss-Bonnet. How should you learn this subject? I don't know. I don't know if I found quite the best treatment. I quite liked the course taught by Richard Hamilton at Columbia University. He had notes and exercises that I thought were wonderful, very, very explicit, all calculation, and just a couple of theorems proven. DeCarmo has a book, Differential Geometry of Curves and Surfaces. That might be fine. I also like this book by an older book by Coxeter, Introduction to Geometry, which starts with a lot of classical geometry, which not a lot of people do, or at least not a lot of people teach anymore. Things like the geometry of affine and projective space and incidence of lines and points and conics, that sort of thing. And of course, people do use this. They use the geometry of projective space in these apps that you take a picture and it gauges your size correctly because it's using projective geometry, and also finite geometries are important in computer science and combinatorics. And he gets into the differential geometry as well. Definitely, take the opportunity to learn about discrete differential geometry and how computer graphics actually work. That could focus your attention on something meaningful and not get lost in the weeds. It's so easy. For example, if you start with a graduate text like DeCarmo's Riemannian geometry, which of course is a great book and contains some deeper theorems, but this is for after you've had all those wonderful examples and building your technique from and a sense of the subject. So what about algebraic geometry? There's a subject that probably some people who are interested in math have probably heard of. Of course, this is the study of the geometry of solutions to polynomial equations like x squared plus y squared equals 1 gives you a circle, but of course, in higher dimensions, things get much more complicated. There are a lot of different ways of coming to this subject. I would say it's not just one subject. Now, you could come to it, you might need different prerequisites depending on how you come to it. Complex analysis, your course in algebra, maybe of course a number theory if you're focused on the problems of arithmetic and finding rational points or points over finite fields that solve these equations. And there's nothing wrong with studying something like real algebraic geometry. What about geometry of polynomials over the real numbers, where positivity makes a big difference and there aren't always that number of zeros? People do use that as well. And maybe if you're coming from physics, there are some period integrals and moduli spaces. In some ways, this theory overlaps quite a bit with differential geometry, but it's approached in a very different way. And I don't know exactly how to recommend that you start doing it. It depends on what you're interested in, where you're coming from. If you really like complex analysis and then you start learning about these elliptic integrals and elliptic functions and start thinking about that function theory and study Riemann surfaces, that's a way in. I mean, that is some very classical, you could call it algebraic geometry, and you want to know there are ways of seeing those spaces as solutions to polynomials. That's a very good theory. I don't know exactly. So maybe there's this book by Markuszewicz, Introduction to the Classical Theory of Abelian Functions, which builds up. I really want a text that builds up from that, how the work of people like Gauss and Abel and Jacobi to Riemann and the Riemann surface concept and some of the algebraic geometry and functions on those Riemann surfaces. there are so many different books on Riemann surfaces. And maybe I like this new book by Donaldson, Riemann surfaces. Another way in could be the book by Clemens, A Scrapbook of Complex Curve Theory. There are other ways. If you're interested in arithmetic geometry, those books I already mentioned when it came to number theory, Silverman Tate, Rational Points on Elliptic Curves, Knapp's book on elliptic curves. There's a book by Stepanov, Codes on Algebraic Curves. Here is a very practical thing that people do with these solutions on algebraic curves for coding theory that could help focus your attention. And you don't need all that much machinery. Here's my worry about algebraic geometry, that with the modern view of this subject, people will be encouraged to learn a ton of formalism, a ton of machinery, to one day learn about practical things, about someday you'll learn resolution of singularities or something you'll actually use, but not until you've learned a whole bunch of stuff that I could never get through. I strongly recommend that you avoid at all, avoid at any cost courses in commutative algebra or things like schemes, just so that you can do algebraic geometry. That only study that if you need it, if you are already studying algebraic geometry. Now, if you're really interested, and maybe if you're coming at this from a classical perspective, I've seen a couple ways of doing this. There's a book by Joe Harris, Algebraic Geometry, a First Course. That looks good. There are people who actually use algebraic geometry concepts computationally. That's another thing. Anything but Hartshorne, frankly, that's what I'm telling you. I guess I learned a lot of what I ended up using from this book by Griffiths and Harris, Principles of Algebraic Geometry. So to summarize what I've told you about these courses and the math major, what I really hope that people do is follow their curiosity. You should only take a course when there's something that you want to know about from that course. Focus on solving problems. It's all, which is what math ultimately is about, not about building theory, not learning some theory for its own sake. Focus on the problems you can appreciate now. And every course should start with a problem that you can appreciate, help to go towards answering that problem, and pose some new problems at the end. So you know that there's a development there. You want to go somewhere that will keep going, not something that's finished. Try, if at all possible, to appreciate how these problems were solved. Don't just look at the finished versions of theories and study definitions that almost always came about after the subject was resolved, because of course, if you're training to be a mathematician, that's the situation you're going to be in. Now, of course, you have to strike some kind of balance. It's not all about history. It's not all about old stuff, because you're trying to get to the forefront. You're trying to do something. The things that you investigate should be active investigations, but you need to strike that balance somehow. There's nothing wrong. It's very good to focus on applications. Again, this will keep your feet on the ground. Study anything, study physics, study computer science as well, study fluid dynamics, study engineering, study the things that people use things for, so you don't, it's not just off in outer space learning whatever math to solve just its own math problem, so you're only talking to yourself. Very good math is done by solving the problems that are right in front of you that you can't avoid. Learn the techniques, it's not all about definitions and theorems, that comes at the end. Learn the techniques in a subject. Use the definitions and theorems to summarize. Obviously, you need some definitions to say what the model is that you're working in the first place, but the key definitions and distinctions that you draw should come out in the form of the proof. And avoid unnecessary abstraction and generalization. You only need the theory that covers what you're talking about. You don't need a language to cover more that you haven't seen yet. It'll be there for when you need it. Something I've discovered by looking over the undergraduate curriculum is that really all these basic subjects cover math that really only gets not much further than 1900. There's really very little 20th century mathematics when it comes to these standard courses. And so you do not need 20th century theory that comes later, certainly to get the results of the 19th century. That is my attitude, is you don't have to take all of these courses. You just study the basics in some of them, find one area that you're really interested in, that you go further. That might be the only one where you go deeper into the 20th century as an undergraduate. And maybe, but probably unlikely, we would be able to get to modern work, but at least so that you can appreciate modern problems in one subject. That's where you should be. If you are there, you're really in a good place, especially if you want to be a mathematician and do your PhD in mathematics. That's really all you have to be by the end of an undergraduate program. You don't have to be so broad. No one's going to give you a prize for knowing it all. You really want to be deep in one subject and be very interested in that thing. And that will help you a lot. Maybe later in your career, having a broader sense of mathematics could help you. All right, that's my take on the math major. Hopefully I've said something you won't hear from other people and is helpful to somebody. Please let me know. All right, thanks a lot.